we're just going to dive right in. I think folks sort of know the drill by now. And just wanting to cover kind of the agenda for today. So we're going to remind people of kind of what we've set out to do in CalTrack 2.1, what topics we were hoping that we'd be able to tackle in this, in this process right now before we move on to bigger and better things in the, hopefully in the CalTrack 3.0 world. And also wanting to give people an update then on some pull requests that have come our way from on the EE weather front and on the OEEM front. OEEM, for those unfamiliar, is OpenEEmeter, which is the code base that actually runs the CalTrack calculations. And EE weather is the code base that effectively pulls in weather data, because obviously we have to have weather data to build these models. And we've had some work on that front from other parties, which we're super excited about and want to highlight in this meeting and get any thoughts or feedback from the broader group on. And then wanted to cover just a few quick topics on the daily model, which has been obviously the source, if you've been at these meetings, of most of our efforts to this point. And we wanted to touch a bit on thermal lag and then talk a little bit more about just kind of results and where we are right now. And then we wanted to spend some time in conveying some of our efforts and what we've learned just recently on isolating seasonal bias and root mean squared error under this cross-validation approach, because it's been important, I think, that we develop this more holistic model, but at the same time, we need to be able to take a step back and probe individual, like isolated performance aspects of the model. And seasonal bias was one of the things we've set out to solve. So we need to understand sort of how we're doing there. And then ultimately that brings up a bunch of questions on what we should be prioritizing. And that's ultimately one of the most valuable things we can get from this group. So we'll have some discussion on some of those topics after we can get through some of that material. So just diving in to remind folks of the goals that we had identified for this specific 2.1 CalTrack process. And for the daily model, I think these things we've covered ad nauseum. I don't really feel like we need to get into it a ton here, but just to summarize, can we improve some of the specific and known areas of model bias, like seasonal bias? And can we make some computational efficiency gains in the process? Because in order to dive in and have a model that is a little bit more complex to enable like solving seasonal bias or weekend weekday bias or these issues, we probably need to add some parameters to the model, and we probably need to add some optimization steps. So the question becomes, can we do that while not making the model so complex that we can't run it at scale on many hundreds of thousands or even millions of meters, which is one of the most important use cases for, at least for recurve. And then on the CalTrack hourly front, there are a handful of small bugs that we know exist in the code, and I think we'll be planning a pull request to remedy some of those little issues that are present. And then also we had set out in the early days of this process with the idea that we would also take advantage of the hourly formulation that exists kind of in the heart of the CalTrack hourly model, but to use that for the demand response use case. For those who are familiar with CalTrack and some of the history around CalTrack, the model was really formulated initially with the energy efficiency use case in mind. And in energy efficiency, you have a specific set of considerations for long-term baselining. You effectively need to understand the consumption pattern of a meter during the entire year, so you can capture seasonal patterns and build those seasonal patterns into an annual model. And CalTrack Daily does that a specific way. CalTrack Hourly does that a different way. But the CalTrack Hourly model itself is set up in such a way that it could be very extensible and amenable to moving to the demand response use case. And Recurve's done some work with KISO on that front, but there's also just more that needs to be contemplated here. But we can also potentially have some easy wins on this front and give people access to a model that does have some specifications built around the demand response use case specifically. And so I think in the next meeting, not this meeting, but just to set the stage for the next meeting, the folks from Watt Carbon and also probably Recurve as well would like to make some proposals to this group around how the Caltrack hourly model can be formulated with baselines that are appropriate for specific demand response scenarios. So I just want to put that out there for folks to think about before the next meeting. It's not something we're going to talk about today, but if you're interested in that topic, I would definitely encourage you to come to the next meeting and help us think through that. And so we had also identified EE weather as a source of potential improvement. And one of the topics that we had identified was the need to extend EE weather beyond the United States and to get to United Kingdom or further sources of international data, and what we might find in that realm as we look to extend EE weather. So we've been really, really happy that the folks at Carbon Co-op have reached out and have dove into this problem and really taken it upon themselves. You know, they're overseas and they're here late tonight for them to talk us through a pull request that they've made on the EE weather front and the OpenEEmeter front to help Caltrack be, you know, run, operated with weather data and like appropriate model parameters for international or the UK specific case. So we're going to hear from them here in just a moment. And then finally, there's been a group, Sealed, that has reached out and has asked, you know, might there be something that we can use, that we can formulate a computation of delivered fuels savings in the Caltrack sort of monthly model formulation. So that's something that, again, we're not going to talk about today, but I want to put that on the radar. For those familiar with delivered fuels, you know, the problem, as I understand it, is typically data for delivered fuel consumption is fairly sparse. So you might have delivered propane, and you know that you know, across the entire summer there was, you know, X amount of propane that was used by a building, but you don't have every single month fleshed out necessarily. So you over the course of a year, you might have 6, 7, 8 data points, but you don't necessarily have 12 data points. So you run into data sufficiency issues in the Caltrack monthly model. So the question has come up, you know, with delivered fuels specifically, is there a way that we can relax some of the monthly data sufficiency requirements and still maintain reasonable performance so that we can track delivered fuels savings? And I think that's a very reasonable question to ask. And so I expect that we'll have some discussion of that next week, probably led by the folks at Sealed. I think it's a good question for us to ponder collectively. So with that, I wanted to open up the floor here for a discussion of the pull requests. And James, if I could pass the baton to you. I don't know if you have any slides to share. If you do, I'm happy to hand the screen to you, or if you have anything you just want to screen share for, or if not, you know, I can just sort of exit out of the deck and we can just have a conversation collectively. What's your needs here?
So I have some slides that I can, if you're happy for me to share my screen, I can just crack on with that.
Yeah, definitely. Okay. Did I stop sharing?
Yes.
Okay.
Just trying to, yeah, okay. Okay, you can see this?
Yes.
Okay, I'll try and keep this as brief as I can. Yeah, so I'll just jump straight into it. So yeah, we're an organization called Carbon Co-op. So we're an energy services cooperative based in Manchester, England. And yeah, we really kind of we're a membership-owned organization, mainly sort of early adopter interested householders looking to try and reduce their carbon emissions and their energy impact. Some of you might be aware that the UK has notoriously drafty building stock. So we've we've received an increasing amount of inquiries and membership over the last year as energy prices have really started to increase. So yeah, and we came into a bit of funding about 8 months ago from Innovate UK, which is a UK government agency, to basically look at Caltrack and think about how we can use Caltrack as the basis of a potential future pay for performance standard over in the UK. So that's really what we've been doing over the past I guess 6 months really in earnest, kind of looking at Caltrack. This is one thread of the broader piece we've been doing on. So I've been leading the kind of technical side of things, but we've also been looking at how actually would you use this as the sort of qualitative side of things, I suppose, on how would you implement this in the UK market and start to think about how you could trial something like this, given the specificities of the local context. But because this is the Caltrack working group, I'm mainly going to talk about the technical stuff. So yeah, I guess the way that Caltrack works, and when I say Caltrack, I mean OpenEEweather and OpenEEmeter collectively. The way that works in the US, obviously we've got these two models, OpenEEweather and OpenEEmeter. OpenEEweather is obviously the weather calling app, and the OpenEEmeter really does the kind of processing of air temperature data and smart metered energy consumption data, and you get your counterfactual from that. But when you try and recreate that in the UK context, obviously because the model was developed over in the US, there are a couple of issues. So first of all, there's no immediate weather data function from OpenEEweather outside of the US. So that was our kind of first stumbling block. And the second stumbling block is really that OpenEEmeter as a model is calibrated to Fahrenheit data only. So the US is really the only country in the world that uses Fahrenheit data, uses Fahrenheit scale. So anybody wanting to use Caltrack outside of the US is going to struggle because a lot of the Fahrenheit scale is very much kind of hard coded into the OpenEEmeter code base. So what we've done basically is we've developed almost a set of standalone additional modules that we've included in this pull request to the Caltrack code base. And I myself and my colleague Matt Fawcett spoke with Phil and with Adam yesterday about the detail of this. But essentially, what we've done with OpenEEweather is we've built in an API through to the Copernicus. So for those who don't know, the Copernicus program is basically a European Union satellite reanalysis weather data program. So it's slightly different to the way that OpenEEweather works already, because the way OpenEEweather works is it calls temperature data from the NOAA database. But we opted for the Copernicus database for a couple of reasons, which I'll go through in just a second. And then secondly, we included a regional toggle on the OpenEEmeter code base, so that you can essentially specify what country you're in, and it'll toggle between Celsius and Fahrenheit and do a couple of other things as well. And essentially that means that you can run the model outside of the US with these amendments. And for those who are interested, there are a set of Jupyter notebooks that I pulled together, kind of setting out how this would operate. But it essentially the amendments are pretty straightforward. It really is just kind of adding into the OpenEEmeter hourly and daily functions, specifying what region you're in. But the key here is that it all defaults to existing OpenEEmeter and existing OpenEEweather. So if you're running OpenEEmeter or OpenEEweather in the US, as most of you will be, it wouldn't make any difference basically at all to the existing model. But what this means for us over in the UK, if we're trying to use OpenEEmeter, this is kind of what your counterfactual would have looked like beforehand, from running OpenEEmeter daily, and you essentially just get a straight line counterfactual. It corresponds to an average of the more or less an average of the training period consumption, and that is basically down to the fact that the model can't decide whether or not it's a whether or not to pick a heating degree day model, a cooling degree day model, or a mix of the two, or whether to just go for a base load only model. And it just goes for the base load only model because it thinks that the it thinks that because it doesn't have temperature conversion, it thinks that the balance point is about 50 degrees Celsius higher than it should otherwise be. But after obviously including temperature conversion, you get much more of a dynamic counterfactual in the way that you'd typically expect with OpenEEmeter daily. And then just comparing the outputs, time-wise outputs for counterfactuals on the running this on a UK basis through to a US basis. There's absolutely no difference between the counterfactuals by running that temperature conversion piece on the daily model. Secondly, we've included, I suppose, secondly, outside of including temperature conversion, we've also included in the hourly model a set of UK specific balance point assumptions, and not just UK specific, but also France, Germany, and Spain. So the idea is now there are these balance point assumptions in here. You can also use that in those countries. We've included we've included heating balance points here. We haven't included cooling balance points, particularly in the UK because nobody uses air conditioning in the UK. It has like a less than 1% penetration in the UK market, so nobody uses it. So I've included 200 degrees Fahrenheit on the cooling balance point there. But similarly, a lot of the nationally recommended balance points in France, Germany, and Spain. I mean, I've included them here, and it also included the references on the Jupyter notebook included with the pull request for those who are interested. And because the balance point assumptions are slightly different for each country. So, I mean, just going back a slide, the US balance point, heating balance point assumption is 50 degrees Fahrenheit, but in the UK it's 60. It just because balance point assumptions feed into the way the OpenEEmeter hourly occupancy matrix works. It basically means that OpenEEmeter hourly will run a slightly different model on two sets of data, and they'll return very slightly different outputs. So yeah, we can see here that they're from the graph that the outputs don't exactly align, and that is basically down to that different heating balance point that's kind of recommended in the literature for buildings in different regions. Jumping on to kind of EE weather and that reanalysis data that I alluded to beforehand. So we've built in an API call through to the Copernicus program, which will return accurate weather data for anywhere around the world, basically regardless of where you are. So with the NOAA data, that's all of the weather data there is taken from weather stations, typically corresponding to airports. That does have worldwide weather data, but I'm not sure whether the weather data outside of the US is of sufficient quality to actually run a model like OpenEEmeter, like whether you can get consistent weather, whether you can make consistent weather calls, not just having hourly weather data, but also actually just potentially missing decades of of 2-meter temperature data, which is going to be problematic. Adam and Phil and I continue to talk about whether we can, whether that stands. But yeah, regardless of that, you still get basically equal access to weather data anywhere in the world, regardless of how close you are to a weather station, or an airport. So for those sites that are further away from weather stations, this is obviously beneficial. And you can also toggle the API to include things like solar irradiance. You can include wind speeds and precipitation as well. So there's a whole range of factors you can get from that. And in terms of the actual data outputs you get from the Copernicus climate data store reanalysis, it stands up very well against the NOAA data in terms of accuracy. So yeah, very much of a kind of minimal variance across multiple years of weather data for similar sites. But there is an issue. It's much slower than existing EE weather. So yeah, whereas EE, it's extremely slow. Whereas you get EE weather from, you can download a 2-year interval call of data for less than a second with original EE weather through the NOAA API, through the climate data store. Partly because of just the traffic on the site. It's used extensively in academia. It can take up to 552 seconds. So we've kind of recommended that users in the United States should basically continue to use the original EE weather, the NOAA API, for that reason. Just a quick description of other stuff that we've been doing. So we've also built a front end, which this is not really worth talking about now, but I'd be happy to speak about anybody interested separately. We've built a front end and we brought it under our existing PowerShaper brand, which essentially uses the OpenEEmeter and the EE weather backend. Just essentially represents that for retrofit analysis and for DNOs evaluating efficiency savings on a large scale over here in the UK. So yeah, just to kind of round up, I suppose, we've got a couple of key questions that'd be good to maybe discuss today. First of all, is there a benefit to future EE Weather International in pursuing a reanalysis approach, principally from that accessibility perspective, I suppose, for those sites that are either in different climate zones or or much further from weather stations included on the NOAA database, or simply are just excluded through existing data constraints on the NOAA weather database. For example, as I mentioned, potentially missing years for certain sites. And secondly, should balance points, I suppose, be hard-coded for international and site-specific usage of EEmeter hourly? And I'm thinking here specifically specifically as to why EEmeter hourly incorporates basically hard codes balance points, whereas obviously EEmeter daily uses a grid search function to find a much more dynamic kind of site-specific balance point approach, which would essentially eliminate some of the variance that you see between regions on the EEmeter hourly piece that I outlined earlier. And then apart from that, I'm obviously more than happy to take questions from the group, and very happy to discuss any of this either here or separately. You can find my details here at the bottom, James at carbon.coop, and similarly Matt Fawcett on very easy to remember, Matt at carbon.coop as well. Just one final thing to say, we're slightly time constrained here. We're running out of funding at the end of March. So if you did want to talk about it, it would just be great to talk in the next few weeks, really, before we start to wrap this up.
Thanks, James. Are there any questions for James and the Carbon Co-op folks in this pull request, and either on the code or code side or on the conceptual side? I can say a few things about Caltrack hourly because we haven't talked about that much to put some of his request in context here. But are there any questions on what he had from the group?
Just filling in on one of James, your questions. Yeah, I definitely see value in the international weather component, internationalization of it. So I can't think of a reason why not to go forward with that part of the request if the code checks out with people who know the code better, obviously.
Yeah, definitely. And there's a lot of interest in advanced measurement of verification and paper performance on this side of the pond, not just in the UK, but also, I mean, some of you, I assume, will be aware that the Sensei project, which was a Horizon 2020 European Union project, just wrapped up, where they developed a separate model to Caltrack, I suppose, as I guess a competitor. But I think our angle is very much that this kind of serves as the precursor, basically what could be a universal standard. So we kind of prefer to go with this one.
Any other questions or thoughts? Awesome. Yeah, Armin has a good question in the chat, James. I'm actually curious about this too. One of the things that we're going to be gearing up for when we're through Caltrack 2.1 and we can turn our attention more fully to the hourly model is the incorporation of solar PV within the hourly model. And I'll just say for folks' context, the hourly model right now does not do a very good job sometimes of modeling solar PV customers because it is a time of weekend temperature model. It is not aware of solar irradiance or cloud cover or the kinds of variables that can have a major influence on solar PV customer consumption on the electric side. And Armin is asking, are you thinking at all about bringing in solar irradiance data? And I'll just lend a little context to that. As we've started some initial work on this, we found that the NOAA database over here is not very reliable for solar irradiance data. And maybe it's even just absent altogether from many weather stations. So we're trying to grapple with where should we be getting solar irradiance data from in order to actually build these models. And I'm curious if I guess we're curious if you've thought at all about that. It's a good question.
So we didn't think about including solar irradiance data just because we've had our hands full. And I know you guys are kind of starting to think about this anyway. So I didn't really want to cross wires, to be honest. But yeah, I've just put a link in the chat to the ERA 5, which I think is environmental reanalysis data. And yeah, you can find everything you need on there. They've also got some not bad API documentation if you want to start having a play about with using that.
Great. Thanks. Well, let me give a last call here for questions, and then we can move on because there is quite a bit more material to get to today, and we'd like some feedback from others on a few other topics. Are there any other questions for James? Great. Well, James, thank you so much. I can tell you we are thrilled and really appreciative that you guys have dug in and done this work and helped improve EE weather and the OpenEEmeter. For those who are not as familiar with the hourly model, because we haven't really dove into it during this working group yet, the hourly model, at least in the United States, has a preliminary regression that is done in order to set some parameters that are used for occupancy detection in both the baseline model and counterfactual. And Phil, correct me if I'm stepping out of turn here, but those fixed balance point temperatures effectively limit the computational complexity of the model and allow us to run the model more robustly and quickly. But those balance point temperatures are obviously not necessarily optimal building to building, and they're not necessarily optimal for buildings overseas. As James mentioned, there are other recommended balance point temperatures for other countries outside of the United States. So it's not necessarily something that causes like massive performance issues in the model, but it is a nuanced aspect of the model where it can have an impact, obviously. So we definitely appreciate that you've done that, James, and you guys have done the research around this and around EE weather as well. So we'll be reviewing this pull request. We've already dove in and have provided some suggestions, but we fully anticipate bringing this on board and making this part of the code base. So thank you so much for the effort. And if those of you on the call have other questions, feel free to reach out to James at those email addresses and Matt as well at Carbon Co-op. Great. Thanks, you guys. Adam. Yeah. So let me get back into the deck here, and let me make sure I can do this right. Here we are. Okay, so that is the pull request topic. So just wanted to spend just a minute or two on thermal lag, just to provide a brief update. And folks may remember during the last call that when we were looking at the inclusion of thermal lag parameters into the preliminary Caltrac 2.1 daily model, we were seeing that those parameters were causing, they were harming the performance of the model. They were causing performance issues. And you can see that in this graph on the left, where the y-axis here is effectively the improvement on a percentage basis in the root mean squared error relative to the Caltrac 2.0 model, like the existing Caltrac daily model. And so this was something that we were fairly confused by. Why would the inclusion of these parameters cause such a performance issue? And in the end, we found out that this was a bug in our code whereby every single Caltrac 2.1 model that was being formulated was including these thermal lag parameters, when the intention is instead to make those parameters only included where the model shows that it is beneficial to include those parameters beyond a penalization term that we're incorporating. So once we remedied that issue, we're now seeing the improvement over the Caltrac 2.0 model when thermal lag is included, and you can see this on the right-hand graph now, makes a lot more sense. So thermal lag is at the very least, it's not causing this huge misbehavior. Although I'll talk a little bit about the fact that it's not necessarily improving things much either in some coming slides. But it's just to say that if folks were confused by this, we were too. And this is just kind of the nature of model development as we're in flight right now. And every few weeks we come share these results. There can be bugs in the code, and this was certainly one of them. So we've remedied this issue, and now I think we have thermal lag that is basically incorporated only when and where the benefit of the inclusion, it outweighs a penalization term that we've included in the model selection. So this is good news. That's all I really wanted to mention on thermal lag. It's just to clear that up. So we wanted to spend a little bit of time and just visit some of kind of where we're at with the full model results at this point. So just to remind people, in the preliminary Caltrac 2.1 model, we have the ability for the model to basically split along weekends and weekdays, as well as split along seasons. So if the model selection criteria allows, if we overcome the penalization term on any of those axes, we can split the model into summer, shoulder, winter, and into weekend, weekday. And each combination of those elements can produce a unique and distinct model for those specific data points. And then we've been using this cross-validation scheme to test whether or not we're seeing improvement over the Caltrac 2.0 model, and pay attention to things like overfitting. So we wanted to just kind of revisit where we're at right now, and then I'll come back and talk a little bit more about some specific trade-offs that we're looking at with respect to seasonal bias, because that's probably the biggest single issue that I think we're trying to solve in Caltrac 2.1 daily. So this slide is just showing results for residential gas meters. And we're looking at a training model versus a training data set on the left, and a training model versus the testing data set on the right. And all of these test versus train splits are determined using that cross-validation approach that we've talked about several times in previous meetings at this point. But what we're seeing is effectively that when we're looking at the root mean squared error, these are all root mean squared error results. And the y-axis, again, is percent improvement over the Caltrac 2.0 model. And each of these violin plots is basically showing us for a model selection criteria. So if we look at the left-hand graph and we look at that sort of the first left of these plots, that is using sum of squared errors as the objective function in the model. So the sum of squared errors we're using sum of squared errors to optimize the model, as done in many models. And we're seeing that for the full population of gas meters, we're seeing roughly a 7-8% improvement in root mean squared error over the Caltrac 2.0 model itself. And this is when we're looking at the training model on the training data set. So when you're in that scenario, you don't quite know how your model would perform on new data. And that's the point of carving out test data from within these samples. So when we take the model developed on the training data and we apply it to the data that's been withheld as test samples within the cross-validation scheme, we see the distributions that are shown in the right-hand graph. So again, looking at the sum of squared errors component of this violin plot, we see a fairly similar distribution, which is a good sign that we're not overfitting the model too much. Now, having said that, you can see that there is a difference between looking at the training data set versus looking at the testing data set. And in particular, you have this long tail where you see degraded performance in a very small number of meters. And that's what you would expect when you have some models that are being overfit. So this is a good sign that everything is sort of stable and looking reasonable. And we are seeing improvement in root mean squared error over the existing Caltrac model. Now, when we look only at the meters for which there was a split that occurred. So, I've mentioned that the model is allowed to split between seasons and weekends versus weekdays. Now we see dramatic improvement over the Caltrac 2.0 model. But the problem that we're trying to understand and wrap our heads around right now is that this split is only occurring for a small minority of meters. So in this residential gas data set, there's only 8% of meters that are being split in any way. So effectively 92% of meters are not being split by season. So the model is just an annual model and they're not being split by week and weekday. So these are just the 8% of meters that are split into some combination of different seasons or different weekends versus weekday independent models. And so upshot here is the reason these models are not just automatically split is we have instituted a penalization scheme to guard against overfitting. And we've talked about that in previous meetings. But we are wondering, is this penalization term potentially too severe? Certainly with only 8% splitting, we are not seeing all that much improvement in seasonal bias, as an example. So do we need to accept some degree of overfitting in order to solve the seasonal bias problem? That's one of the things we're contemplating right now. And if we look also at the commercial electric sector, then again, we're looking at something similar here. These are all the meters and sample that we're studying right now. We have a trained data set and a test data set through cross-validation. Again, we're certainly seeing some improvement in the model, but we're not seeing an enormous improvement, but we are seeing this much sort of more significant positive tail in these distributions. So a number of these meters are improving by 40-50% over the existing Caltrac daily model. So there's definitely reason for optimism here. And the majority of those meters in those long positive tails where we're seeing a lot of improvement over CalTrack daily are meters that are being split. So again, split by season or week in, week day, or whatever it is. So, and we're seeing again that when we look at training versus test data, we're not seeing substantially different shapes of these distributions, which again is a good sign that at least at this point, we're not encountering a high degree of overfitting of these models. So this is a good sign. So one thing I do want to point out is when we look both at root mean squared error and on the right-hand side now we're looking at mean absolute error, we see substantial improvement in both of these areas. But when we look at thermal lag, which is the pink color right-hand distribution within both of these plots, we're seeing, and these are both test samples now, so we're just purely looking at the test data. We're seeing some degradation of model performance versus not including thermal lag in the model. So when we're looking specifically at the test samples where now we're in a predictive kind of scheme and we're looking at model performance on data we have not seen before, we're seeing that the thermal lag parameters are inducing some degree of overfitting, worse model performance. So this is something that we're, at this point in time, I think we're leaning toward, well, we either have to choose between doing a lot more research into thermal lag or leaving thermal lag by the wayside for the moment and coming back to it in potentially CalTrack 3.0 or further R&D, or if other people want to sort of pick up that baton and really propose an approach around thermal lag. We're just not seeing the benefit of including a bunch of, of including even 2 thermal lag parameters in the model. We're seeing that it's actually causing the model some degradation. So let me stop there because I've kind of blitzed through a bunch of results. And then we can come back to this topic of looking at seasonal bias and RMSE under cross-validation, where we're really specifically looking at that trade-off. But I wanted to see if anybody had questions or thoughts on what I've presented just in the last 10 or 15 minutes here.
Is there a possibility that some of the degradation when you're going into test when using lag is sort of a metering measuring thing where you're basically getting some target leakage into the predictor?
Help me understand the target leakage. What do you mean by target leakage?
Yeah, so target leakage is anytime you're training on data and something that you wouldn't actually know in the general case is showing up in your predictor variables where it should only be in your target variable. And it can be, sometimes it can be kind of subtle, like a condition flag that is related to the ultimate outcome in some way.
Mm-hmm.
I was trying to think through what might be happening here, and I was wondering if maybe the way the metered data is actually collected, some of what you think is on, sort of your target day is actually consumed pre-target day, during the lag period. And I'm wondering if that may be something that's going on there. I don't know the mechanics of how metering is going on.
My initial impression, and Armin, I'd like to get your thoughts on this as well if you have some thoughts. My initial impression is we're doing everything we can, I think, to try to guard against those kinds of, well, I guess in this case, we're just using a penalization term and we're looking at the model performance under the cross-validation scheme. So potentially something like that could leak through. That's an interesting thought. I don't know that we have insight into what that might be. I mean, we certainly don't have insight into what that might be.
Okay, so
yeah, Armin, please jump in. Yeah.
Will, are you talking about like using extra data in the thermal lag, for example, in in the train test, and then somehow we were using it in tests, and then that impact the result for the test data?
No, I'm thinking more along the lines of it might show up in well, I guess it would show up in both. Anyway, so what I'm thinking is, you've got your gas consumption up to the point where you say, okay, that's historical. Now I need to predict sort of the future, or at least the baseline for this day. And I just my thought is like, well, what if you're actually measuring a couple hours into your baseline day?
We don't look at it as a time series based sort of thing. So that's basically use temperature as the kind of x-axis, or the way that as our predictive variable rather than the time. So we're not blocking the data by the time.
Oh, that's right. Okay. Yeah. Okay. It's been obviously been a while since I dug around the code.
Oh, that's a good thought though. I mean, yeah, it's worth kind of wrapping your head around that notion. We in developing the cross-validation scheme talked quite a bit about this concept that really we're working with time series data, but the model itself is not sort of a time series model. It's like Armin said, like that x-axis is not date time. I mean, you can plot it that way, but really the model formalism is one of temperature.
Yeah.
Yeah, it's a good, but thank you for the question. And if you have other thoughts on this, we're definitely keen on hearing. I think what we're trying to do here is not let the perfect be the enemy of the good. And one of the things that I wish I had some time to present some statistics on this week, but maybe next week I can come back and present some statistics on this. Where we saw thermal lag become a real issue was when you had the previous day's temperature was significantly different than the current day's temperature that you're predicting or that you're modeling. So if today is the subject of your model, but yesterday was 10 degrees colder and you're in the heating degree day zone, like you're in heating, you're lower than the heating balance point temperature on both days, then yeah, thermal lag is real. You can see it. But the question is sort of how severe is it and how frequent is that effect? Because in order to model that effect, you have to add additional parameters, of course, and those additional parameters come at a cost. They come at a cost of inducing a higher degree of overfitting, and they come at a cost of making the model more computationally complex and more conceptually complex. So we're trying to grapple right now with what are the elements of this model that really need to be in there versus ones that may not. And ultimately, we're striving for a model where only the parameters that are included for any given meter are those that are proving to be useful in modeling that meter. So in that sense, thermal lag doesn't necessarily have to be, an eyesore, like a sore thumb for the model. But we're struggling to figure out exactly right now whether or not to put a lot more effort into this right now, which would sort of delay things and push everything back, or do we want to just kind of say, look, this is something that we've done some research on. Our initial attempt wasn't probably beneficial for this model, so we're going to put a pin in it and come back to it at a later date, or we're going to put in the time and effort now. So I think that's an open question. Would be curious folks' thoughts on like how important this really is in the grand scheme of things. No model is going to be perfect, of course. So I think what my inclination is to kind of leave it be right now, because there just aren't a ton of days where it's 10 degrees colder yesterday than it is today. I mean, obviously that happens, but they're not like the majority of days or anything like that.
I think Adam, if I can chime in on the importance, and I know that the primary goal here is about energy efficiency, but there's some applications that we're using OpenEEmeter to look at efficiency and beneficial electrification measures in the context of utility distribution planning. And so there's only a handful of hours where it makes a difference, but those are basically the only hours that they care about. And so the fact that we have this really systematic error in OpenEEmeter for the peak hours, essentially, you know, I mean, we're sort of living with it for now, but it's definitely awkward, right? I don't want to go back to a DR baseline for energy efficiency measures because it doesn't make any sense at all. But it's definitely important for those hours from a utility perspective that it's so far off. And I don't know that. Yeah, and that is for the hourly method. That's totally fair, Armin. So,
well, that was my question for you, Ethan. Is the hourly method really where we should be focused to tackle this problem? Because it, you know, the longer we spend on it here now, then the further out in time we actually worry about it in the hourly model itself.
yeah, I'm certainly happy to focus on fixing that in the hourly model instead. Although it seems like, well, I don't know if it's more challenging or not. So I won't.
I don't know either. Yeah, we don't know yet, honestly. It's not something we really contemplated in the hourly model yet, but it does just kind of beg the question if your use case is more specific around the hourly model, then maybe that's the best forum to tackle it in, as opposed to now. Not to say that if we tackled it in the daily model, potentially we would learn something very useful for the hourly model. But yeah.
No, that's totally fair. Can I ask one other question, which is just the similarity of these distributions? I find a little bit unsettling, and you sort of framed it up as like, oh, we're comforted by this, and unless maybe I missed something along the way, but like, shouldn't we see different performance of these different approaches relative to? I mean, I know we see a little bit here now as we're getting into some of the, you know, these later slides, but it's frankly surprising to me that the distributions have been so similar, and I wonder whether that suggests that there's like some underlying structure in the errors that Caltrack has, like in, you know, the current 2.0 Caltrack, that it's producing some kind of weird errors in each model, and these are all not having those errors, and so they're all fixing the same error at the same time or something. Like, it's just bizarre that they're so similar.
You mean, are you talking about like within like the left-hand graph as an example, the fact that the distributions within the left-hand graph are very similar? Or are you speaking about the fact that the distributions are similar between these two graphs?
No, similar between the two graphs, I'm not surprised about, but just that the four, and maybe I got confused somewhere. These are like four different proposed alternative formulations for the model, right?
These are, yes, well, these are four different, well, they're four different optimization schemes for the model, really.
Right.
So it's like, are you looking at sum of squared errors? Are you looking at L1 loss, which is just, you know, absolute error, or are you looking at an adaptive function, which is sort of a mix of the two? For, you know, Travis would hate me for simplifying that in that way, but, you know, that's effectively what we're looking at. And then the third one is just kind of sum of squared error, where you have thermal lag, and the left-hand one is sum of squared error where you don't. You certainly see a difference between those two in the shape. But I think the reason it's not, to me, it's not terribly surprising that these are similar is just that what it's telling us is that the specific choice of how you optimize the model is not necessarily super important for the final model formulation. Yeah.
Basically, the difference between the sum of squared error and L1 is how you deal with the anomalies. So imagine a function, a U shape that we have like in the Caltrack, like how we change the slope of one line will be decided by the L1 or L2. So the way they deal with the anomalies, it changed a little bit the slope of the line. So it's not going to change drastically when you see in from the population level, because that slope is a little bit changing.
Yeah.
For each meter.
I think where we would start to see, but Ethan, I think what your comment is making me ponder here is, I mean, I am a big fan of doing the kind of smell check kind of research just to make sure everything's operating as you anticipate it to be operating. So while I'm not surprised necessarily that we're seeing similar distributions given different loss functions. What I would like to see potentially is if we drastically changed one of these to be some, you know, empirical function that was just a flat line or something, who knows, that we would get a dramatically different distribution. And if that was the case, then I think it would give us some comfort that there's not some crazy bug in the code or something like that. So
yeah, that's a great idea. The other suggestion that I would have is, I mean, the distributions are the same. It doesn't necessarily mean that the same exact meters
that's
are
right.
having the same change under each case. So it'd be really interesting to see sort of like pairwise comparison between all the models and answer the question of whether like all of these new models are coming up with exactly the same predictions and Caltrack is 5%, 10%, 20% off on the exact same ones, or whether there's not a lot of correlation and it just happens that there's about the same number that are off by 20% in each one, which would be surprising, but maybe that's just the shape of the universe and I can get used to it.
Yeah, you know, I think this question of which loss function we should ultimately be using in optimizing the model is an open question. And it's one of these things that we keep saying, oh, we're going to dive into that really deep this week or next week or whatever it is. But ultimately, we've prioritized other things, but that's coming. Just know that that's like, this is very much in our minds. We have to make a decision around one of these functions, right? Like at the end of the day, the Caltrack model needs to be one of these things, not all four of them.
Totally.
So we have to make a decision. So we're definitely going to be diving in a bit. So noted, I'll just say noted right now. We'll come back to it.
Thank you.
Great. So let me move us on here because I think we're really excited actually about this next section. And Armin has done a lot of good work burning the midnight oil to get some of the data that I'm about to present together over the last few days. So what are we trying to do here? Like, we've been talking a lot about the sources of bias in the Caltrack daily model. Now, I mentioned earlier that if we just kind of back up a few slides, we're looking at the gas results here, and we're seeing that only 8% of the meters under the current penalization function are being split in any way. And our question is, well, is that really the best that this model can do? What would happen if we just sort of force splitting upon this model? Are we going to see like a big degradation in some aspect of model performance, like RMSE, for example? And I think we need to take a step back and really just isolate that aspect of the problem in order to educate ourselves about what is the fundamental limitations under which we're working. So what we've done in the last few days is to basically pull out just the model itself and the stochastic gradient descent that optimizes like heating degree days and balance points, and what it optimizes balance points and slopes and things like that, and determines, you know, within any given submodel. So if you have 3 seasons, summer, shoulder, and winter, you have a model within each of those seasons that needs to be optimized with balance point temperatures, slopes, things like that. So we just pulled out the sort of fundamental Caltrack 2.0 model, essentially. And now what we're going to look at is what seasonal bias looks like when you allow for splitting, not only allow for it, but when you force splitting. And we're still going to look at a cross-validation scheme. So we're looking at train data and test data, but we're going to be focused on the test data here. So we're talking about the predictive capacity of the model. So this is what Caltrack 2.0 looks like. And we're focused on 500 meters right now. So distributions aren't like perfectly smooth, but we're seeing that on the left-hand graph, we're looking at winter bias. And this is just a distribution of individual meters and the degree to which the winter model was biased. So if there's a data point at -10, then that's telling us that across the entire winter, there is a -10 therms bias in the model. And so we're seeing, I think that if I remember right, the number was something like winter bias was like -14%. So 14% of total consumption. Here we're just looking at it on an absolute basis. But just if you're thinking in percentages, this amounts to about 14% of total consumption. And in order to balance out this wintertime bias, then the model has to make up for it during other seasons of the year. So on the right, I'm showing summertime bias. And you can see that the summer is exactly the opposite. Now we're biased upward. And I haven't shown it here, but the shoulder distribution looks a lot like the summer distribution. So again, this is no seasonal splitting. This is effectively just looking at the Caltrac 2.0 model. And I just want to point out that under this model formulation, it is the most simple model. And we are actually optimizing these models under cross-validation. So we're sort of cheating in a way. We're saying, you know, in the final model, cross-validation might be too computationally intensive to use it. So we need to effectively try to emulate cross-validation with a penalization term on the addition of new parameters. But right now, we're just actually optimizing these models under cross-validation. So take that as a grain of salt. But we're seeing the exact kind of behavior that we would expect to see that we've known exists in the Caltrac 2.0 model. Now, if we instead force the model to split along all of the seasons, summer, shoulder, and winter, now we look at winter bias and on the left and summer bias on the right, we see effectively as a population level, zero bias or very, very small bias in the summer and in the winter. And this is what you would expect because, hey, you're formulating a different model for each season. So that model within that season should not be biased. So in essence, this is a good smell test just to check that if we take our existing formulation of this model and we split it by season, we should not see bias within any of those individual seasons. Now, the question becomes like, what is our sort of fundamental limitation we're working under? And that's where we can turn to some of these error metrics like sum of squared error. So when we're looking at sum of squared error, in this case, we see the average annual test sum of squared error is 482 terms squared, I suppose. But here it's 511.6. So this is good news. We're actually seeing that even when you remedy seasonal bias, you know, again, under cross-validation, we can do so and still see on the test sample a lower sum of squared error. So to me, this gives me a lot of optimism, but this is a solvable problem. Like this is something that if our models are formulated well and we have an optimized penalization function, that we should be able to solve seasonal bias and still have a reasonable within a reasonable degree of like overfitting versus underfitting kind of thing. And then finally, just one other thing I'd point out is we also took a look at different model formulations where we would split winter separately from summer and shoulder, or split summer separately from winter and shoulder together. And when we look at a model where we've split out winter and we formed an independent Caltrac model in the winter versus the summer and shoulder period, then very interestingly enough, you know, as you would expect, again, the winter looks good because winter is being modeled independently, and you can see that in the left-hand distribution. But when we look at summer is now significantly biased. So it seems to me in a way that we probably, maybe the question is actually more about like maybe there's a solution here where we just simply need to be splitting along all the seasons potentially. Or there's some kind of a solution where we indeed allow the model to split according to like a penalization function like we have been doing, and we only allow the model to split when it is proving to be beneficial. I think that's a good thing for us to include in the final model. This is again just kind of giving us a smell check on like, is this a solvable problem or not under a reasonable degree of like sum of squared error. So I'll stop there. that's basically what we wanted to cover today. And then I have a slide just on some questions that we're grappling with that we could get some feedback on. But let me just stop there and see if people have any questions about this. Or Armin, if you wanted to add anything, just feel free to add anything, or if I mischaracterize something, please feel free to jump in.
No, just an idea that just came to my mind based on your presentation. We might optimize the penalization factors based on the population level while we are reducing seasonal bias. At the same time, we're reducing the annual RMSE. So we have, for example, for SoCal gas, like we're like optimizing just based on the whole population. We have some penalization factor for that data set. And then based on cross validation, and we can optimize it for that and then use it in the reporting year.
Yeah, and that's actually a question I have on the next slide that we should contemplate. Mm-hmm. Yeah, does this make sense to folks? Are people scratching their heads, or does this seem reasonable? I'm curious to see any feedback on this analysis and what it might mean for us.
Hey, this is Ken. Can you answer Ethan's question in the chat?
Oh, let's see. What was Ethan's question? Somebody read it.
What does the seasonal split do to the balance points and the base load relative to annual models and the individual meters?
So are you thinking, Ethan, about like the computation of heating and cooling loads and things like that?
Well, I guess what I'm trying to figure out is whether the fix that we're doing here is giving us something that seems realistic from like a engineering standpoint, right? Like we would expect it to reduce the bias because the model is trying to reduce bias, and now we've told it to reduce around the particular categories that we care about seeing it in, and like, hooray, the model does its job. And so my question is like, does this produce crazy outcomes, right? Like I sort of have some sympathy for the idea that people might use their thermostat a little differently, or that there's something else going on that would explain why we would see a little bit of difference. But if we're seeing a different model, then that has to mean we've got different balance points and different base load, and I guess to some degree the slope as well, right?
Yeah.
Okay, Armin, that's fair. But I guess I'm curious, like how big those changes are and what kind of changes they are, and do they sort of match? Like, can we tell a story about why this better matches the world and doesn't just overfit?
Yeah. So first of all, I think the fact that when we split the model into 3 seasons under in this scenario, and we still are able to get lower root mean squared error on the test sample specifically, is an indication that I do not think we're fundamentally limited by like overfitting, at least to solve the seasonal bias problem in isolation. As soon as we mix in weekday weekend bias and thermal lag and smoothing parameters and the other kinds of stuff that we've been looking at, potentially that we are much more limited in that sense. So when it comes to model complexity, one of the things model complexity versus an optimal model in my mind would allow us to split in the ways that individual meter would dictate. So we're looking at gas meters right now, and what we've seen in gas specifically is that seasonal bias is a much more severe issue than on the electric side. Seasonal bias on the electric side is fairly minimal. But what is a much more significant issue on the electric side is weekday bias. And that's particularly true for commercial meters. Sure. So if the model is to be consistent between electric and gas meters, which would certainly be a desirable feature, then to me, you have to have some kind of preliminary optimization step in the model where you're choosing how the model splits. Because I think it's still our strong suspicion that if we just split along every axis we can imagine, weekend, weekdays, seasons, smoothing, thermal lag, we just toss all that stuff in the model, it's bound to be overfit. It's bound to be a hopelessly overfit model. So On the gas side, it's a nice area to study because gas consumption is a little bit more, it's a little simpler than electric consumption, especially you don't tend to have that cooling degree day region. But when it comes to like seasonal bias and why it exists, well, first of all, I would just mention again that the reason we're so interested in solving seasonal bias, especially for gas meters, is it's not a small effect. It's a substantial effect, right? I think I mentioned earlier that, yeah, seasonal bias in the Caltrac 2.0 model during the winter is a 14% effect. The model is under predicting winter consumption by 14%. That's a lot. And it's not something I feel like we should be ignoring if we're diving back into this model. So it's a problem that we're trying to solve. If it was 2%, I'd probably argue that, that's just, tough cookies. It's 2%. We're just going to deal with that kind of thing. But at 14%, I would say we should feel compelled to see if we can solve that problem. It may not be a solvable problem, but I'm optimistic that it is.
I support solving it, and I think we could potentially have a story about what is behind it and why this better fits reality instead of just adding complexity. And I guess partly I'm asking this question because I'm starting to do things with the balance points and base loads and things like that are trying to inform folks who are actually working on these projects and give us more nuanced sorts of evaluation and compensation. And so I'm trying to figure out, like, are we just sort of headed down the path toward the machine learning models that we used to scoff at and say, well, those are uninterpretable and we lose important meaning. And so, like, do we still have, like, what do we think the balance points, let's just stick with balance points for now, like, what do we think the balance points mean under this circumstance? And, like, have you looked at how much they're changing under these different seasons?
I think we need to redefine the balance point. Specifically, if we separate the seasons, for example, balance point in winter, in my opinion, should be different from the shoulder, as I saw in a couple of models. And the slopes are different, but the points of the temperature in the balance points in terms of classic Caltrac 2.0, they're in different locations in terms of temperature. So I think we need to have separate definition inside of each segment of the data, which right now we have seasons. So this is cooling point in the winter, this is a heating point in the winter, or something like that.
Yeah, and I think the reason I brought this graph back up, which I keep bringing up in almost every meeting, but it's kind of hard to wrap your head around. But encoded in these error profiles, I think, is the information that the winter season, for at least at a population level, this is showing us very clearly that the bulk of the error in the daily model in the winter is occurring right around the balance point temperature. And specifically, the model is dramatically under predicting consumption right around that balance point temperature, again, in the winter. And the opposite is true in the summer. So that's just telling us very simply that on average, if your Caltrac model, your annual balance point temperature is, say, 65 degrees, then in the winter, that is a substantial underestimate. And in the summer, it's an overestimate. So you can have a 60-degree day in the summer, but you're going to tend to not actually kick on your heater. Whereas in the winter, you could have a 70-degree day and you are going to kick on your heater. And the balance point temperature of 65 just kind of misses symmetrically in order to get balance across the annual model. So we know that this is an effect, and we see it very specifically in this error profile. So I didn't know until we looked at these plots that was specifically what was happening. But it's very clear that that actually is what's happening. And then when we look at a number of individual meters, we see this pattern emerge in like the vast majority of meters. So, you know, when we look at, again, I think somewhere in here, I have this graph, right? Like here's the Caltrack 2.0 distribution of seasonal bias. So when we're looking at that population level summary of the error profile, you don't know whether it's like one or two crazy outlier meters, or is it a systematic issue across all of the meters or most of the meters. And these graphs just show us, you know, this is a systematic issue. Like the vast majority of meters are experiencing this effect. So the upshot is there are genuinely different balance point temperatures that should be assigned in the winter versus the summer versus the shoulder. So in that sense, creating a new model for each season is kind of the natural solution. It's not necessarily the only solution, but I think hopefully that helps answer some of your question, Ethan. I hope I'm not dancing around it too much.
No, I mean, I'm bought into the idea that we should try to address this. It's definitely a significant problem, and thermal lag would have been a more, it would have felt more elegant, right? Because it would give an explanation for why you don't, you know, deal with a hot day in the winter or a cold day in the summer the same way that you do in other seasons, in a nice physics way that that doesn't require us to create new models. But I see we're having trouble making that pan out, and so, you know, this also potentially answers it because you change your thermostat settings, and, you know, or you keep the windows open, or, you know, there's certainly some stories there. And I guess I was just trying to have a better sense for what this might, like how dramatic the change in some of those factors is. Remind me, we're doing hourly basis degree days, right? For when we're actually doing degree days, because like that's the other thing that makes a big difference around the balance points. Is that true?
So that's a super interesting question. Let me, I'll actually pull something. We got a few minutes here. I'm going to pull something up real quick and share it with everybody, because that's something we've looked at, and it's pretty fascinating in my mind. Give me just 'cause I just have to find it. Give me 2 seconds.
Sure.
Hey, while you're pulling that up, Adam, I've been digging around in energy and buildings from 1986, which is when Mimi and Robert Socolow and Meg Fells were just putting out the Prism stuff. Yeah. And there's an article. I'll send this. It's nowhere available unless you go dig in the archives. But I can send a PDF of this to Adam, and he can distribute it. Yeah. But there's an article called "Seasonality of Non-Heating Consumption and Its Effects on Prism Results," and they actually, you know, I didn't have a chance to read it, but they actually talk about, well, whatever. I think it's relevant, and it's relevant to the wider context of just how far away, as we go into the machine learning, how far away from the kind of the underlying kind of physical engineering model that, you know, that was what motivated Prism originally, which is effectively what, you know, Caltrack is. You know, how far away we go from that, and what it means, and what, you know, what the reference points mean, and everything else. So this is the whole issue with 7 or 8 articles in it. I'll send it around. I kind of assumed you guys had access to this stuff. If not, it's actually super interesting, and it's like hand-drawn graphs and shit. It's
no, I love
very,
it.
very
definitely
bespoke.
Send that on. You know, it's kind of funny. Your comment, Ken, makes me just kind of recollect about being like, I can't tell you how many times when I was in physics and I was at the point of writing a research paper that I would do like a full literature review, and I would find that like some scientists from the 70s had literally solved the problem, right? and I've got all these modern tools and like lasers and stuff at my fingertips that they never had, but they were just clever enough to figure it out. So I wouldn't be surprised. So if something from my face, definitely send it on. Would love to look at that.
Ken, do you have the whole? I think that's a whole special issue of that journal that you're talking about. Do you have the whole thing, or just the one article?
I have the whole thing. I will send it along.
Cool.
Awesome.
Because Prism, by the way, was originally just for natural gas usage. So they were like, I don't know if this is ever going to work for electricity.
Oh, but this, I mean, they've got electric in here. I mean, this is.
Yeah, I think by this point they had started, but that whole special that's like the Bible. That whole special issue of that journal goes into all of this, is like the foundation for like everything that came subsequently.
Yeah, I'm, I feel bad now that I didn't kick this out. I mean, I haven't had it forever because it took us. We actually had to hand copy this from Mimi's paper version. But yeah, I'll pass it around, and I highly recommend it, even just for the historical fun of it. But yeah, I'll send it over to Adam.
Definitely, thanks, Ken. We'll circulate it with the group. So if you can send it our way, as long as it's cool with you, I'll send it on to everybody.
Copyright hopefully has expired. Yeah, I mean, we used to talk about the lighting being one of the big, seasonal non-heating loads, but I think that's probably fading a lot now that we're seeing incandescence sunset, and certainly it doesn't give us any explanation about why the gas, unless we've got homes out there with gas lighting still, and that's probably even more rare.
Yeah, I hope there's not too many of those left, for sure. Well, let me leave you all with just kind of something to wet your whistle, or just some food for thought here. So Ethan, your question just reminded me of this. Can you see this graph here? This is just another graph. Okay. I never know with Google Meet if I don't get like confirmation that I'm actually sharing. So I always have a nightmare scenario where I'm not. So this was something I did a while back, so just give me a moment to remember what I did here. But the x-axis is our same, like, average temperature minus heating balance point, and we're looking at a population of meters here. So this isn't just 1 meter; these are many thousands of meters. I think these are also the gas meters. Yeah, these are definitely also the gas meters. And so what the bottom graph is showing is heating degree days in the black line, and then heating degree hours in the blue dots. For example, this is again winter in blue, summer in red, and shoulder in green. So basically, you see a curved profile in heating degree hours, and you see more or less. I mean, I think if I zoom in, this is actually curved here because it's, again, a population, but it's like you see, well, I don't know about that. It's basically linear and then linear for heating degree days around the balance point temperature. And it's curved for heating degree hours. Now, the heating degree hours makes sense, right? I think what I'm centering this on is the daily balance point temperature. So if the balance point temperature is 65 degrees and you're at 64 degrees, then you have 1 heating degree hour according to heating degree days. But if you're at 65 degrees average daily temperature, then you might have a whole bunch of hours that are at 50 degrees, 52 degrees, or whatever. And then you have other hours that are above that, right? 75, 76 degrees. So heating degree hours shows up earlier because the days over here on the right side of the balance point temperature are just days where at least some of the hours were above or below your balance point temperature here. So that's why you get this curved profile. And the error, like the difference, like I've scaled the difference between the heating degree days and heating degree hours, and that's shown here. So this is like the scaled difference. And this top graph is the actual Caltrac daily model error. Looks pretty similar, doesn't it? So, this is something that we just haven't kind of followed through on because there's just a million things to look at. And our thought was, well, look, we could. The problem with this is you still have to determine a balance point temperature. So you still have to run a model to determine a balance point temperature for any given meter. But if you run that model and you determine that balance point temperature, then the error profile, or the difference between heating degree days and heating degree hours, is at least around the balance point temperature, fairly closely emulates the actual error in the daily model. The reason I think we haven't pursued this is it's this extra modeling step. So the computational complexity increases a lot, but potentially this is something we would want to pick back up.
It doesn't require more model runs though. It just means that when you're creating the matrix for feeding into it, you have to apply the deltas on the 8760 instead of deltas on the 365. So it's slightly bigger matrix subtraction that you're feeding into it, but the actual model optimizations doesn't require any more steps because you don't have to look at any more gradations in balance point necessarily. So it's a tiny bit slower, I would guess, but it's really just a little more subtraction. I doubt that's actually the bottleneck on it.
Yeah. So yeah, I'm just staring. That's a good point, Ethan. And just staring at this, I think another thing that sort of dissuaded us is, well, the error profile in the winter is so closely, looks so close to the scale difference between heating degree days and heating degree hours. The summer and shoulder, they kind of have different patterns, right?
But we're looking at a heating only. I'm sorry to interrupt you, Adam.
Oh, go ahead.
We're looking at a heating only profile, and earlier you were pointing out that the error that we probably see in the summer months is just the model sort of carrying over and compensating and trying to minimize bias into the summer. Yeah. So I feel that, and like it certainly would be more comforting if everything just pops into place. But I mean, the error around the heating degree day balance point for the summer months is not all that influential in terms of the overall error in the model. I think what will be interesting is to see how the model lets the summer shake out if the winter fell into line.
If the winter fell into line, that's a good point. It's a very good point. Well, okay, food for thought, everyone. I know we're at time, so thanks. I definitely appreciate that everybody is giving us your thoughts here. Like, it's exactly what we need, and we'll reach out with the next set of meeting info and all that kind of stuff. And I'm really hoping that in the next month or so we can sort of pin down some of these things and start to approach the group with kind of like final recommendations. But we're definitely still, like, it gets more complex before it gets more simple, and I think we're in that phase right now, and we're trying to figure some of these things out. So bear with us, and just having the chance to have these like open discussions is incredibly helpful for us. So thank you everybody for that, and we'll be reaching out again. And Ken, if you do pass that on, please do. I'll send it on to everybody, and we'll go from there. So thank you to everyone.